Hello, everyone, and welcome to Bookercast, the podcast where books come to life.
And I'm so excited to dive into another amazing story with all of you.
Whether you're a bookworm or just love a good story, this is the place for you.
Every episode, we explore incredible books, talk about their stories and characters, and share insights that'll make you fall in love with reading all over again.
All right, let's not keep you waiting any longer. Get comfortable, and let's jump right into it.
Sounds good.
Welcome to our deep dive into Brian Greene's The Elegant Universe.
Oh, a fantastic choice.
It's theoretical physics.
Yes, it is.
But Greene is like this expert guide,
Right.
He takes these really complex ideas like string theory and makes them, understandable.
Yeah.
And even exciting to read about.
Absolutely.
It's really no wonder that the book became like a phenomenon. It really sparked the public's imagination about, what could be beyond our everyday reality.
It definitely did. The Elegant Universe. It's not just a physics book.
Right.
It's an invitation to think differently about the universe and our place in it.
Yeah.
And Greene, he takes us on this intellectual adventure through the history of physics,
Right.
showing us how these brilliant minds clashed over these seemingly impossible questions.
Yeah, and that's where the core conflict comes in, right? This clash between the two pillars of modern physics, Einstein's general relativity, which explains gravity on a cosmic scale, and quantum mechanics, which governs the subatomic world.
Exactly. Think of it like this.
Okay.
General relativity, it's like a smooth flowing river.
Okay.
It explains the graceful movements of planets and stars. But zoom in to the level of atoms and particles.
Yeah.
And you enter the quantum world,
Right.
a world of sudden jumps and inherent uncertainty, more like a bubbling brook.
Okay.
And Greene, he does a fantastic job of illustrating how these two theories,
Yeah.
though incredibly successful in their own domains, just don't play nicely together.
Right. It's like trying to fit square blocks into round holes.
Yes, exactly.
And this conflict, it becomes even more apparent in extreme environments.
Yeah.
Like black holes
Yeah.
and the Big Bang,
Absolutely.
where both gravity and quantum effects are at play.
Precisely. Imagine a car trying to go from 0 to 60 in an instant.
Whoa.
That's the kind of breakdown we see. When we try to combine general relativity and quantum mechanics in these extreme situations, Greene, he uses the analogy of a car redlining to really bring this conflict to life for the reader.
It's a great analogy. You can practically hear the engine sputtering,
Yes.
and it makes you realize why physicists are so driven to find a more fundamental theory.
Yeah.
One that can harmonize these seemingly discordant ideas.
And that's where string theory comes in.
Yes.
The star of the Elegant Universe.
String theory.
It's this radical proposal that replaces those point-like particles we're used to
Right.
with tiny vibrating strings.
Uh,
And what's so elegant about string theory is that it naturally incorporates gravity,
right.
unlike previous attempts at unification.
Okay, so string theory, it's like a grand symphony
Mm.
with all the forces and particles of the universe emerging from the different ways these strings vibrate.
That's a beautiful way to put it.
Yeah.
But there's a catch, and it's a big one. String theory requires the existence of extra spatial dimensions beyond the 3 we experience daily.
Okay.
Not just 1 or 2, but 6 more.
6 extra dimensions.
Yes,
Now that's a concept that really stretches the imagination.
it does.
It's hard to even fathom what that would look like.
Right.
I mean, if they're really there, why don't we see them?
Greene anticipates that question perfectly.
Okay.
He uses the analogy of a garden hose.
Okay.
From a distance, it looks like a simple line.
Yeah.
But up close, you see it also has this curled up circular dimension.
Okay.
In string theory, these extra dimensions,
Yeah.
they're thought to be curled up into tiny compact spaces,
Uh-huh.
far smaller than anything our current instruments can detect.
So these extra dimensions, they could be all around us.
Yes,
But we're just too big and clumsy to notice them.
precisely.
That's both fascinating and a little unnerving.
It is, isn't it?
Yeah.
And what's even more intriguing is that the specific way these extra dimensions are curled up, their geometry, could determine the fundamental properties of our universe, like the types of particles and forces that exist.
So it's like the shape of these tiny curled up spaces
Yes,
sets the stage for the entire cosmic drama.
exactly. And that's just one of the many mind-bending ideas that Greene explores in The Elegant Universe.
Yeah.
But to really grasp the scope of string theory, we need to delve into the historical context
Yeah.
that led to its development.
You're right.
Yeah.
Let's go back in time
Okay.
and trace those intellectual threads that led physicists to this radical new way of thinking about the universe?
It all starts with this seemingly simple question.
Okay.
What is the universe made of?
Yeah.
For centuries, philosophers and scientists pondered this fundamental mystery.
Right.
The ancient Greeks,
Yeah.
with their idea of atoms,
Uh-huh.
they took the first steps towards a scientific answer.
Right.
But it wasn't until the late 19th and early 20th centuries that things really heated up.
Right, with the discovery of subatomic particles like protons, neutrons, and electrons.
Exactly.
I remember those planetary models of the atom
Yes.
with electrons whizzing around the nucleus like tiny planets orbiting the sun.
Revolutionary breakthrough.
Yeah.
But it turned out to be just the tip of the iceberg.
Oh.
Yeah, as physicists probed deeper, they discovered a whole zoo of even more fundamental particles. Quarks, leptons, and even antimatter.
Wow.
It was like peeling back layers of an onion,
Okay.
revealing this hidden world of complexity.
So much complexity.
Yes.
And with these new particles came the realization that there are 4 fundamental forces governing their interactions.
Yes.
Gravity, electromagnetism,
Uh-huh.
the strong force, and the weak force.
Precisely.
Right.
And this quest to understand these forces and particles
Yeah.
led to some of the most dramatic shifts in scientific thinking, particularly with the development of quantum mechanics and relativity.
Yeah.
Greene does a fantastic job of highlighting these breakthroughs, showing how each one challenged our intuitions about the universe and pushed the boundaries of human knowledge.
Right. And it's this clash between general relativity and quantum mechanics.
Yeah.
That need to reconcile the smooth cosmic dance of gravity with the jumpy, uncertain world of the very small.
Yeah.
That really sets the stage for string theory, right?
Exactly. String theory emerged as this audacious attempt to bridge the gap between these two seemingly incompatible pillars of physics.
Okay.
But to really appreciate the elegance and audacity of string theory,
Yeah.
we need to dive deeper into the weird and wonderful world of quantum mechanics.
Okay, let's take that plunge, because quantum mechanics,
Right.
that's where things get really strange, isn't it?
It certainly is.
It's a world where particles can be in multiple places at once.
Yes.
Where uncertainty reigns supreme and where reality itself seems to be more like a fuzzy cloud of possibilities than a sharp, well-defined picture.
It's a world that defies our everyday intuitions. But it's also a world that has been confirmed by countless experiments.
Wow.
One of the most baffling concepts is wave-particle duality.
Right.
The idea that light and matter can behave like both waves and particles, depending on how you observe them.
So it's like saying a baseball can act like a ripple in a pond.
It's a mind bender, isn't it?
It really is.
Greene uses the famous double-slit experiment to illustrate this idea.
Okay.
You shine a beam of light, or even fire individual electrons, through 2 slits.
Okay.
And instead of seeing 2 bright spots on a screen behind the slits,
Right.
you get an interference pattern, as if each photon or electron went through both slits simultaneously.
How can a single particle be in 2 places at once?
It seems impossible, doesn't it?
It does.
And that's the crux of quantum mechanics.
Yeah.
It forces us to abandon our classical notions of particles traveling along neat, well-defined paths.
Right.
Instead, we have to think in terms of probabilities and wave functions, which describe the likelihood of finding a particle in a particular location.
So it's like saying we can only predict the odds of where a particle might be.
Exactly.
Not its exact location.
Precisely.
And this inherent uncertainty.
Yeah.
This is captured in Heisenberg's uncertain principle, right?
Yes, it is.
That's one of the defining features of quantum mechanics.
Absolutely.
And it tells us that there are fundamental limits to what we can know about the universe at the subatomic level.
Yeah.
We can't simultaneously know both the position and momentum of a particle with perfect precision.
You got it.
So there's a certain fuzziness
Yeah.
built into the fabric of reality itself.
It's unsettling, but also incredibly profound.
Yeah.
Yeah. And this quantum fuzziness, it has profound implications for our understanding of the universe.
Yeah.
It means that the universe is not deterministic.
Right.
Things don't unfold in a predictable clockwork fashion.
Right.
Instead, there's an element of randomness and chance woven into the very fabric of reality.
Yeah, it's a radical departure from the clockwork universe of Newton,
It is.
where everything was thought to be predictable if you knew the initial conditions.
Exactly. Quantum mechanics throws a wrench into that deterministic worldview.
Right.
It tells us that the universe is inherently unpredictable.
Yeah.
There's a certain wildness at its core.
Yeah.
But this wildness doesn't mean it's chaotic or meaningless.
Right.
It simply means that we need a new set of rules, a new way of thinking to understand it.
And that's where the genius of people like Niels Bohr and Werner Heisenberg comes in.
Absolutely.
They developed the mathematical framework that allows us to make sense of this strange quantum world,
They did.
even if it defies our common sense intuitions.
Exactly. They gave us a way to calculate the probabilities of quantum events, to predict the behavior of particles and atoms, even if we can't say for certain where they'll be or what they'll do.
It's a remarkable achievement,
It is.
considering how counterintuitive these ideas are. And it's this bizarre and beautiful world of quantum mechanics that really sets the stage for string theory, right?
Absolutely. String theory, with its radical proposal of tiny vibrating strings,
Yeah.
it emerges as a potential solution to unify quantum mechanics and general relativity
Okay.
to harmonize those discordant notes of the cosmic symphony.
Okay, I'm ready to dive into that harmony.
Let's do it.
But before we get lost in the strings, let's take a step back and explore the other pillar of modern physics, Einstein's theory of relativity.
Excellent point.
It's a theory that revolutionized our understanding of space, time, and gravity.
It did.
And it plays a crucial role in setting the stage for string theory.
It does. We need to understand the landscape that string theory attempts to unify,
Right.
and that includes the mind-bending world of relativity.
Right. Okay.
So let's start with special relativity,
Okay.
which emerged from Einstein's quest to understand the nature of light.
I've always been fascinated by the idea that the speed of light is this cosmic speed limit.
Yeah.
That nothing can travel faster than, 186,000 miles per second.
It's quite a concept.
It just seems so arbitrary.
It does seem that way, doesn't it?
Yeah.
But Einstein showed that this seemingly arbitrary speed limit, it has profound implications for our understanding of space and time.
Okay.
He realized that the speed of light is constant,
Right.
no matter how fast you're moving.
Wait, so if I'm chasing a beam of light at, say, half the speed of light, the light is still moving away from me at the full speed of light.
That's exactly right. It seems counterintuitive,
It does.
but that's the essence of special relativity.
Okay.
And to accommodate this constancy of the speed of light,
Yeah.
Einstein had to reimagine the very fabric of space and time,
Okay.
showing that they are not absolute, but relative,
Right.
depending on your frame of reference.
So it's like saying there's no universal clock ticking away for everyone. That time is more like a river
Yeah,
flowing at different rates depending on your motion.
that's a beautiful analogy.
Fine. Yeah, and this relativity of time leads to some truly mind-bending consequences.
Right.
Like time dilation, where time slows down for objects moving at speeds close to the speed of light.
Right.
Greene uses vivid thought experiments to illustrate these effects, making them surprisingly accessible.
Yeah, I remember him describing those muon experiments,
Yes.
where subatomic particles called muons, created high in the atmosphere, actually reach the Earth's surface despite having a very short lifespan.
Right.
And it's because time slows down for them
Yes.
as they travel at nearly the speed of light.
Those muon experiments, they are a striking confirmation of time dilation.
Wow.
And then there's length contraction,
Yeah.
where objects appear shorter in the direction of motion at relativistic speeds.
So it's like the universe is playing tricks on our perception of reality.
It makes you wonder if there's even such a thing as objective reality.
Yeah.
When space and time are so fluid and malleable, it's a profound question that continues to fascinate physicists and philosophers alike.
It certainly does.
And it's one that string theory attempts to address in its own unique way,
It does.
by proposing that the very fabric of space-time might be woven from these tiny vibrating strings.
Exactly.
Okay, my mind is already starting to bend.
I can imagine.
But before we dive into those strings, let's finish our exploration of relativity by tackling Einstein's other masterpiece,
Yes.
general relativity, which brings gravity into the picture.
Excellent point. General relativity is truly a monumental achievement, arguably the most beautiful theory in all of physics.
It's the theory that explains how gravity works,
It is.
not as a mysterious force acting at a distance,
Right.
but as a consequence of the curvature of space-time itself.
Precisely.
Right? I remember Greene's analogy of a bowling ball on a rubber sheet,
Yeah.
how the ball's weight warps the sheet,
Uh-huh.
creating a dip that causes nearby objects to roll towards it. That's how gravity works, according to general relativity, right?
Exactly.
Massive objects like the sun warp the fabric of space-time around them,
Uh-huh.
and planets like the Earth simply follow the curves of that warped space-time.
That's how it works.
It's a brilliant way to visualize gravity,
It is.
and it highlights the deep connection between matter, energy, and the geometry of space-time.
Absolutely, but it also raises some profound questions about the nature of reality itself.
Like what?
Well, if space-time is this dynamic, malleable fabric
Yeah.
that can be warped and curved by massive objects,
Uh-huh.
what does that mean for our perception of the universe? Is
Yeah.
our experience of space and time just an illusion? A
Right.
consequence of the particular way our brains interpret these cosmic wrinkles?
Those are big questions.
They are.
And I'm guessing string theory has something to say about them.
It does.
Well-
String theory, with its proposal of extra dimensions
Right.
and its potential to unify gravity with the other forces,
Yeah.
offers a radically different perspective on the nature of space-time itself.
Okay.
But before we dive into those depths,
Yeah.
I think it's helpful to connect these mind-bending concepts back to our everyday world.
You're right. It's easy to get lost in the abstract when talking about relativity and quantum mechanics.
It is.
But these theories, they have real-world implications, don't they?
Absolutely.
Yeah.
Think about GPS technology, for instance.
Okay.
It relies on incredibly precise clocks onboard satellites orbiting the Earth.
Right.
And those clocks are affected by both special and general relativity
Okay.
because of their motion and their distance from Earth's gravitational field.
Wow.
Without accounting for those relativistic effects,
Yeah.
GPS wouldn't be nearly as accurate.
Wow. So relativity isn't just some theoretical curiosity.
No,
It's essential for something as commonplace as GPS navigation.
exactly. And that's just one example.
Yeah.
These theories underpin many of the technologies we rely on in our modern world. From lasers and transistors to nuclear energy and medical imaging.
It's amazing how these seemingly abstract ideas about space, time, and the quantum world have had such a profound impact on our lives.
It really is.
Yeah.
And that's part of what makes the study of physics so compelling. It's not just about understanding the universe for its own sake,
Right.
but also about uncovering the fundamental principles that govern our world and shape our technological advancements.
Okay, I'm ready to dive back into the deep end.
Right.
Let's finally tackle the core concept of the elegant universe.
Let's do...
String theory.
String theory is where things get really wild, but also incredibly beautiful.
Okay.
It's a theory that attempts to weave together the seemingly disparate threads of general relativity and quantum mechanics
Yeah.
to create a tapestry of the universe that's both elegant and profound.
I'm on the edge of my seat.
Great.
Let's unravel this cosmic tapestry and see what patterns emerge.
Yeah.
Okay, last time we explored the wild world of quantum mechanics.
Yes, we did.
And delved into the mind-bending realm of relativity.
Right.
Now we're ready to tackle the heart of Brian Greene's The Elegant Universe.
Okay.
String theory.
Yes.
It's this incredibly ambitious idea that aims to be the theory of everything, right?
Exactly. And the elegance of string theory
Yeah.
lies in its simplicity at its core.
Right.
It says that everything in the universe,
Right.
from the smallest particles to the largest structures, is made up of these tiny vibrating strings.
Yeah, I remember Greene comparing it
Yeah.
to a violin string.
Uh-huh.
Depending on how you vibrate the string, you get different notes.
Right.
And in string theory, those different notes correspond to the different particles and forces
Exactly.
we observe in the universe.
That's a great analogy. But here's the kicker.
Okay.
For string theory to work mathematically,
Uh-huh.
it needs more than just the 3 spatial dimensions we're familiar with.
Okay.
It needs extra dimensions.
Right.
Curled up into tiny spaces so small we can't detect them.
6 extra dimensions.
Yes.
Yeah, that's a concept that's really hard to wrap my head around.
I know.
How can something be real if we can't even see it?
It challenges our everyday intuitions about space and dimension, that's for sure.
It does.
Greene, he does a fantastic job of explaining this
Okay.
by asking us to imagine an ant
Okay.
crawling on a garden hose.
Right.
From far away, the hose looks like a line. Just one dimension.
Okay.
But to the ant,
Yeah.
there's another dimension.
Right.
The circular dimension it can walk around.
Uh-huh.
String theory says our universe could be like that hose
Okay.
with those extra dimensions curled up so tightly.
Okay.
We only experience the familiar 3.
So those extra dimensions, they could be right under our noses, so to speak.
They could.
But they're just too small for us to perceive directly.
Exactly.
It's like a hidden world within our own.
Right.
But if we can't see them, how do we even know they're there?
That's a great question.
Yeah.
And it gets at the heart of one of the biggest challenges facing string theory.
Okay.
It makes predictions about phenomena
Uh-huh.
that happen at incredibly high energies,
Okay.
far beyond what we can achieve with our current particle accelerators.
Yeah.
So direct experimental verification
Right.
is extremely difficult.
So for now, string theory,
Yes.
it's mostly a mathematical framework, this
Yeah.
beautiful set of equations that seems to fit together consistently.
Right.
But how did physicists even come up with this idea of strings in the first place?
It's actually a bit of a detective story. Back in the 1960s,
Okay.
physicists were struggling to understand the strong force,
The strong force.
the force that binds quarks together inside protons and neutrons. And they found this mathematical formula
Okay.
that seemed to describe the strong force interactions.
Yeah.
But it was a mystery why it worked.
So they had a formula that fit the data, but they didn't know what it meant.
Exactly. But
Right.
then a few physicists realized
Okay.
that if you modeled particles as tiny vibrating strings, you could derive that same formula naturally from the string's behavior.
Really?
It was like finding a missing piece of a puzzle.
Wow. So string theory was originally meant to explain just the strong force.
That's right.
Oh.
But then things took an unexpected turn.
Okay.
String theory predicted the existence of a massless particle with 2 units of spin.
Okay.
That's exactly the kind of particle we'd expect to carry the force of gravity, something called a graviton.
So string theory, almost by accident, predicted the very particle that could unify gravity
Yes.
with the other forces. That's pretty wild.
It was a major turning point.
Wow.
Suddenly, string theory wasn't just a theory of the strong force.
Right.
It was potentially a theory of quantum gravity.
Wow.
The holy grail of modern physics, a way to reconcile Einstein's theory of gravity with the quantum world.
But didn't string theory also have some problems early on?
Yes, it did.
Yeah, I remember Greene talking about how it predicted particles that weren't observed in experiments.
You're right, it wasn't all smooth sailing.
Yeah.
But instead of abandoning the theory,
Yeah.
physicists kept digging deeper.
Okay.
And what they found was that the inconsistencies
Yeah.
could be resolved by introducing a concept called supersymmetry.
Supersymmetry? Okay. That's a new one for me.
It's a pretty mind-blowing idea.
Okay.
It says that every known particle has a superpartner particle
Okay.
with a different spin.
All right.
Think of it like a mirror image of the particle world.
So for every electron,
Yes.
there's this electron. For every quark, there's a squark. It sounds like something out of a comic book.
It does sound a bit fantastical, doesn't it?
Yeah.
But supersymmetry has some very appealing features from a theoretical standpoint.
Okay.
It helps to stabilize the equations of string theory
Uh-huh.
and even provides a potential candidate for dark matter.
Right.
That mysterious stuff that seems to make up most of the matter in the universe.
So it's a theory that could solve multiple mysteries at once.
It could.
That's pretty elegant if you ask me.
It is quite elegant.
But have we actually found any evidence for these superpartner particles?
That's the million-dollar question.
Right.
Physicists have been searching for them for decades,
Yeah.
using powerful particle accelerators like the Large Hadron Collider.
Uh-huh.
But so far, no superpartners have been directly observed.
So it's still a waiting game.
It is.
Hoping for that experimental breakthrough that could confirm supersymmetry.
Yeah,
And by extension, bolster the case for string theory.
exactly. But even without direct experimental proof, string theory has already had a profound impact on physics and mathematics.
Really?
It's led to new insights into the nature of black holes,
Right.
the origin of the universe, and even the very fabric of space-time.
Okay, I'm ready for more mind-blowing insights.
Right.
Let's delve deeper into how string theory tackles those big cosmic questions.
Okay, let's start with black hole.
Black hole.
Those enigmatic objects that have captivated the imagination of scientists and the public alike.
Yeah.
For a long time, black holes were seen as these cosmic vacuum cleaners, sucking up everything that got too close, even light.
Right.
But string theory has provided a new perspective, hasn't it?
Yes, I remember Greene talking about how string theory can actually describe the microscopic structure of a black hole.
Yeah.
It's not just this empty void,
No, it's not.
but a complex dynamic system made up of vibrating strings.
Exactly. It's like taking apart a clock
Okay.
to see how all the gears and springs work together.
Yeah.
String theory allows us to peer inside a black hole
Wow.
and see how it ticks, so to speak.
And what's remarkable
Yeah.
is that string theory's calculations of a black hole's entropy, a measure of its disorder, match perfectly with earlier predictions from general relativity and thermodynamics.
They do.
So it's like two completely different approaches
Right.
to the same problem,
Yeah.
arriving at the same answer.
Exactly.
That's got to be a good sign, right?
It is.
Right.
It suggests that string theory is on the right track, that it's capturing something fundamental about the nature of gravity and black holes.
Okay.
And it also has implications for one of the biggest mysteries surrounding black holes,
Yeah.
the fate of information that falls into them.
Right, the famous black hole information paradox.
Yes.
Does information get destroyed when it enters a black hole, which seems to violate the laws of quantum mechanics?
Right.
Or is it preserved somehow?
Yeah.
Which is what most physicists believe.
It's a question that has puzzled physicists for decades.
Yeah.
And string theory, with its concept of a holographic universe,
Right.
offers a potential solution.
A holographic universe. Okay. Now that's a term I've heard thrown around a lot,
Yes.
but I'm not sure I fully grasp it.
Think of a hologram,
Okay.
how it can create a three-dimensional image
Right.
from a two-dimensional surface.
Yeah.
The holographic principle, inspired by string theory, suggests that something similar might be happening in our universe.
Okay.
The information about a three-dimensional region of space,
Uh-huh.
including a black hole,
Yeah.
might be encoded on a two-dimensional boundary,
Okay.
like its event horizon.
So it's like the information about everything inside a black hole is projected onto its surface, like a cosmic movie playing on a spherical screen.
That's a great way to visualize it.
Yeah.
And this holographic principle,
Mm-hmm.
it has profound implications for our understanding of gravity and the nature of reality itself.
Wow.
It suggests that our experience of three dimensions might be an emergent phenomenon,
Okay.
arising from a more fundamental two-dimensional description.
Wow, that's a head spinner.
It is.
So string theory is not only trying to unify the forces of nature,
Right.
it's also redefining our understanding of space, time, and the very fabric of reality.
That's the beauty of it. It's a theory that pushes the boundaries of our imagination and forces us to reconsider our most basic assumptions about the universe.
Okay. My mind is officially stretched to its limits.
Oh, I can imagine.
But there's one more big cosmic question I have to ask about.
Okay.
The Big Bang.
All right.
How does string theory explain the origin of the universe itself?
That's a question that has intrigued cosmologists for generations.
Right.
The standard Big Bang theory,
Uh-huh.
which describes the universe expanding from an incredibly hot, dense state,
Right.
has been incredibly successful in explaining many of our observations.
Right.
But it leaves some big questions unanswered.
Like what caused the Big Bang in the first
Yeah.
place?
Yes.
And why is the universe so smooth and uniform on large scales?
Right.
It's like taking a cake out of the oven and finding it perfectly evenly cooked,
Yeah.
even though you didn't stir the batter.
Exactly. And that's where string theory comes in.
Oh.
It offers some tantalizing clues
Yeah.
that could help us solve these cosmic puzzles. One idea is that the universe might have gone through a period of rapid expansion
Yeah.
called inflation in the first fraction of a second after the Big Bang.
Inflation.
Yes.
So like a cosmic balloon inflating at super speed.
Precisely. And this inflationary period, driven by the energy of a hypothetical inflating field,
Okay.
could explain why the universe looks so smooth and uniform on large scales.
Okay.
It's like stretching a wrinkled sheet of fabric until it becomes perfectly flat.
Okay. I can see how that would work.
Hmm.
But how does string theory fit into this inflationary scenario?
Well, string theory
Yeah.
could potentially provide a natural explanation for the inflating field
Okay.
and the dynamics of inflation itself. It's like
Yeah.
string theory is providing the fuel and the engine for this cosmic expansion.
So string theory might hold the key
It might.
to understanding the very first moments of the universe.
It's a possibility that has many physicists excited.
Right.
And it shows how string theory is not just about unifying forces and particles,
Right.
but also about unraveling the deep history of the cosmos, from its fiery birth to its eventual fate.
This is all so incredibly mind-blowing.
Uh-huh.
And string theory is painting this grand sweeping picture of the universe,
Yeah.
connecting the smallest scales to the largest, the quantum world to the realm of stars and galaxies.
It's amazing.
But I have to ask,
Yeah.
is it all just a beautiful mathematical fantasy? Will we ever be able to prove or disprove its predictions?
That's the ultimate challenge, isn't it?
Yeah.
String theory is a work in progress,
Right.
and it's likely to remain so for many years to come. But even if we never achieve direct experimental confirmation,
Yeah.
its exploration has already enriched our understanding of the universe in profound ways.
Okay.
And it's inspired a whole new generation of physicists and mathematicians to push the boundaries of what we know.
Right.
And to ask even bolder questions about the nature of reality.
Brian Greene in The Elegant Universe has done a phenomenal job of capturing that sense of wonder and excitement.
Absolutely.
He's made these complex ideas accessible and engaging for a wide audience,
He has.
showing us the beauty and the mystery that lie at the heart of theoretical physics.
He really has, and that's one of the book's greatest achievements.
Yeah.
It's not just a textbook or a technical treatise.
Right.
It's a work of science communication at its finest, inspiring countless readers to delve deeper into the universe and to marvel at its elegance and complexity.
Well, this deep dive into the Elegant Universe has certainly left me with a lot to ponder.
I bet.
We've explored extra dimensions, wrestled with quantum weirdness, and contemplated the origin and fate of the universe.
It's a lot to take in.
It is. What else is in store for us in this final part of our journey?
Well, we still have so much more to explore, including the mind-bending concept of dualities and string theory, the implications of a multiverse, and some of the philosophical questions raised by these radical ideas.
Okay, I'm ready for the grand finale.
All right, let's do it.
Let's wrap up our exploration of the Elegant Universe and see what final insights await us.
Okay, so we've journeyed through these mind-boggling realms of quantum mechanics and relativity.
Yeah.
And we've explored this elegant framework of string theory.
Right.
But the Elegant Universe doesn't stop there.
Doesn't.
Brian Greene, he takes us even further down the rabbit hole, exploring some truly profound and philosophical implications of these ideas.
Yeah, we've touched on the concept of a multiverse.
Yes.
This possibility that our universe is just one of many.
Right.
Perhaps an infinite number of universes coexisting alongside our own.
It is a mind-boggling concept.
It is.
It emerges naturally from string theory.
Right.
Especially when you consider those extra dimensions and the vast number of ways they could be curled up.
Yeah, it's an idea that really boggles the mind.
I know. It's hard to wrap your head around.
If there are infinite universes out there, does that mean anything is possible? I mean, are there universes where gravity works differently?
Potentially.
Or where time runs backwards?
It's definitely a question that sparks the imagination.
It does.
And Greene, he certainly doesn't shy away from exploring those possibilities.
Right.
He talks about how the different ways those extra dimensions can be compactified in string theory could lead to this vast landscape of potential universes, each with its own unique set of physical laws.
Right. So our universe, with its particular set of laws that allow for, stars and planets and life as we know it, might just be one random book in that cosmic library.
It's a humbling thought.
It is. It's even a little unsettling.
It challenges our anthropocentric view of the universe, that's for sure.
It does.
But some physicists, they find it liberating. Instead of seeing our universe as the only game in town, we can view it as part of a grander, more diverse cosmic tapestry.
Okay, so that perspective, it could be both awe-inspiring and terrifying.
It can be both.
But if our universe is just one of many, does that diminish its significance? Does it mean our lives are less meaningful?
That's a deep philosophical question.
It is.
And there's no easy answer.
Right.
But I think Greene would argue that the possibility of a multiverse doesn't diminish the wonder of our own universe.
Okay.
It just adds another layer of mystery and complexity. And it invites us to ask even bigger questions about the nature of existence itself.
It's like realizing that the world is much, much bigger and stranger than we ever imagined.
Exactly.
And that there's so much more out there to discover and explore.
Absolutely.
Speaking of exploration,
Yeah.
one of the things that struck me about the Elegant Universe is the way Greene weaves together physics, mathematics, and even philosophy.
He does.
He's not afraid to tackle these big ideas and connect them in unexpected ways.
Absolutely. He seamlessly blends scientific rigor with a sense of awe and wonder. using these vivid analogies and thought experiments
Right?
to make complex concepts accessible to a wider audience.
It's true. He's not just explaining string theory.
Yep.
He's inviting us to participate in this intellectual adventure,
Yeah.
to join him on this quest to understand the universe at its deepest level.
Exactly.
And that's what makes The Elegant Universe such a compelling read.
Mm,
It's not just a science book.
right.
It's a story about human curiosity,
Yeah.
about our relentless drive to push the boundaries of knowledge and to grapple with the ultimate mysteries of existence.
You're right, Greene. He captures that spirit of scientific inquiry beautifully.
He does.
He shows us how science is not just about cold, hard facts and equations,
Yeah.
but also about imagination,
Right.
creativity, and
Yeah.
a willingness to embrace uncertainty.
And it's that embrace of uncertainty that really resonates with me. We've talked about how string theory makes these predictions that are incredibly difficult, if not impossible,
Right.
to test with our current technology.
Yes.
So in a sense, it's a theory that's ahead of its time.
It is.
It's pushing the boundaries of what we can know and measure.
Exactly. And that's where the concept of duality comes in.
Right.
Something Greene explores in the later chapters of the book.
Yeah.
It's the idea that seemingly different theories, different ways of describing the universe
Yeah.
can actually be equivalent,
Okay.
just different facets of the same underlying reality.
So it's like looking at a diamond from different angles.
Mhm.
You see different facets, different colors,
Yeah.
but it's still the same diamond.
That's a great analogy.
Yeah.
And Greene, he describes how physicists have discovered these surprising dualities within string theory itself,
Right.
connecting seemingly disparate versions of the theory
Yeah.
into a more unified framework.
Right. It's like finding these hidden passageways
Yeah.
between different rooms in this vast mansion,
It is.
revealing unexpected connections and symmetries.
And these dualities.
They aren't just mathematical curiosities.
Right.
They have real implications for how we understand the universe.
So they're important.
They are very important.
They suggest that our notions of space and time, the very fabric of reality,
Yeah.
might be more fluid and interconnected than we ever imagined.
It's a profound concept.
It is. It's like realizing that the map we've been using to navigate the universe is just a crude approximation of a much more complex and beautiful terrain.
Exactly. So string theory,
Yeah.
it's not just a theory of everything.
Right.
It's a theory that's forcing us to rethink everything we thought we knew about the universe.
Yeah. Well, Brian Greene has certainly challenged my assumptions with the Elegant Universe.
Me too.
He's opened my eyes to a universe that's far more vast, strange, and beautiful than I ever imagined.
It's an incredible book.
It is. It's a book that has stayed with me long after I finished reading it.
Mm.
And it's one that I'll continue to revisit and ponder for years to come.
I think we all will.
You know, it's a book that sparks the imagination, inspires curiosity, and leaves you with this sense of awe and wonder about the universe and our place within it. Whether or not string theory ultimately turns out to be the theory of everything,
Right.
its exploration has already enriched our understanding of the cosmos in profound ways.
Yeah.
And it's a testament to the power of human ingenuity and our insatiable desire to unlock the secrets of the universe. And that's a wrap for today's episode of BookerCast. We hope you enjoyed diving into it as much as we did. Thank you so much for spending your time with us. Your support means the world, and we can't wait to hear your thoughts on this episode.
Don't forget to subscribe, hit that like button, and share this episode with your fellow book lovers. And let us know your thoughts in the comments below. We love hearing from you. See you in the next deep dive. Bye for now, and happy reading.